Previously, we talked about the theory of inflation and how that leads to Max Tegmark's Level 1 multiverse. Today, we will be looking at the next level of the multiverse, or the Level 2 multiverse as proposed by Tegmark, and some of its defining characteristics. Now, we saw in the previous video that inflation generally refuses to stop and keeps creating more space. This idea is taken a step further with the theory of chaotic eternal inflation. The phrase chaotic eternal refers to what happens on the very largest of scales. According to this model, space as a whole is stretching and will continue to do so forever, but in some regions, it may stop stretching and form distinct bubbles, like gas pockets in a loaf of rising bread. Infinitely many such bubbles can emerge. Each of these is an embryonic Level 1 multiverse, which is infinite in size and filled with matter deposited by the energy field that drove inflation. So, an infinite set of these distinct Level 1 multiverses, some perhaps with different space-time dimensionality and different physical constants, constitute a Level 2 multiverse. But these different bubbles are more than infinitely far away from Earth, in the sense that you would never be able to get there even if you traveled at the speed of light forever. The reason for this is that space between our bubble and its neighbors is expanding faster than you could travel through it. So your descendants will never get to see their identical copies elsewhere in the Level 2 multiverse. For the same reason, if cosmic expansion is accelerating, as observations now suggest, then they might not even see their alter egos in the Level 1 multiverse. So as mentioned before, some of these bubbles or Level 1 multiverses may have different laws of physics. Now, that may seem impossible at first, but not according to Max Tegmark's definition of these laws. He separates the laws of physics into two distinct categories: the fundamental laws of physics, which by definition hold anywhere and any time, giving rise to a complicated physical state of affairs, and the effective laws of physics, inferred by self-aware observers that may vary from place to place. For example, a fish that has lived its entire life in the ocean might make the mistake of thinking of water not as a substance, but as empty space. What a human would think of as a property of water, say the friction when swimming through it, the fish might misinterpret it as a fundamental law of physics. It may even come up with statements such as a fish in uniform motion ends up at rest unless flapping its fins. So this fish would probably have no idea that water can exist in three different phases: solid, liquid, and gas, and that what it believes to be empty space is simply the liquid phase, which is a particular solution to the equations describing water. Similarly, there is a ton of evidence that this is exactly how things are for us. Not only does our empty space seem to be a sort of medium, but it appears to have way more than three phases, perhaps about 10 to the power of 500 or even infinitely many, which opens up the possibility that in addition to curving, stretching, and vibrating, our space may even be able to do something analogous to freezing and evaporating. So the Level 2 multiverse is far more diverse than the Level 1 multiverse. The bubbles vary not only in their initial conditions, but also in seemingly unchangeable aspects of nature. The prevailing view in physics today is that the dimensionality of space-time, the qualities of elementary particles, and many of the so-called physical constants are not built into physical laws, but are the outcome of the processes known as symmetry breaking. For instance, theorists think that the space in our universe once had 11 dimensions, all on equal footing. Early on in cosmic history, 3 of them partook in the cosmic expansion and became the 3 dimensions we now observe. The others are now unobservable either because they have stayed microscopic, with a donut-like topology, or because all matter is confined to a 3-dimensional surface or a membrane, or simply brane in the 11-dimensional space. Thus, the original symmetry along the dimensions broke. The quantum fluctuations that drive chaotic eternal inflation could cause different symmetry breaking in different bubbles. Some might become 4-dimensional while others could contain only 2 rather than 3 generations of quarks. In addition to such discrete properties as dimensionality and fundamental particles, our universe is characterized by a set of dimensionless numbers known as physical constants. Some examples include the electron-proton mass ratio, and the cosmological constant, which appears to be about 10 to the power of -123 measured in Planck units. There are models where also such continuous parameters can vary from one post-inflationary bubble to another. But the question still remains, how can we be sure that the level 2 multiverse really exists? Well, for Tegmark, although we cannot directly interact with other level 2 parallel universes, cosmologists can infer their presence indirectly because their existence can account for unexplained coincidences in our universe. Suppose you check into a hotel and are assigned a room at random and note that this is the year you were born. At first, this may seem like a coincidence, but after a moment of reflection, you would conclude that this is not so surprising after all. The hotel has hundreds of rooms, and you would not have been having these thoughts in the first place if you had been assigned a room with a number that meant nothing to you. The lesson here is that even if you knew nothing about hotels, you could infer the existence of other hotel rooms to explain this coincidence. Another example Tegmark provides is relating to the mass of our sun. The mass of a star determines its luminosity, and using basic physics, we can compute that life as we know it on Earth is possible only if the sun's mass falls into the narrow range between 1.6 times 10 to the 30 and 2.4 times 10 to the 30 kilograms. Otherwise, Earth's climate would be colder than that of present-day Mars or hotter than that of present-day Venus. The measured solar mass is 2.0 times 10 to the 30 kilograms. At first glance, this apparent coincidence of the habitable and observed mass values appear to be a wild stroke of luck. Stellar masses run from 10 to the 29 to 10 to the 32 kilograms. So if the sun acquired its mass at random, it had only a small chance of falling into the habitable range. But just as in the hotel example, one can explain this apparent coincidence by postulating an ensemble, in this case several planetary systems, and a selection effect, the fact that we must find ourselves living on a habitable planet. Similarly, what applies to hotel rooms and planetary systems applies to parallel universes as well. Most, if not all, of the attributes set by symmetry breaking appears to be fine-tuned. Changing their values by the tiniest amounts would have resulted in a qualitatively different universe. So, although the degree of fine-tuning is still debated, these examples suggest the existence of parallel universes with other values of the physical constants. So, if the level 2 multiverse covers all possible initial conditions and symmetry breakings, then surely this is the point beyond which there can be nothing else, right? Well, not according to Tegmark. He goes beyond a level 2 multiverse, which he refers to as a level 3 multiverse. But that is a discussion best left for another time. If you enjoyed this video, do leave a like, share, and subscribe to our channel for more content ahead. Is our universe truly infinite as predicted by inflation, or just extremely large and finite? Let us know your thoughts down below. Until then, we'll see you in the next one.